Hey everybody, my name's Max. I'm here to talk to you about our work about high-dimensional calibration. Joint work with Noah, Mariar, and John. I want to introduce calibration through the setting of binary calibration, okay? In the setting of binary calibration, imagine that you are a weather person, and you are tasked with sequentially forecasting the rain. Each day, you produce a forecast and then observe this binary outcome, whether or not it rained. You could write that down. You repeat, each day producing a new forecast, observing a new binary outcome. You do this for capital T days, and your goal as a forecaster is to be calibrated. What does that mean? It means that if you look back at all the days you forecast 20%, it empirically rained on about 20% of those days. Similarly, if you look back at all the days you forecast 30%, it empirically rained on about 30% of those days. The setting we can consider in this paper is a setting in which you're trying to do calibration even when these binary outcomes are being selected by an adversary who is trying to mess with your calibration as much as possible. Okay, at the offset, this isn't possible because the adversary could simply make it rain if you forecast less than 50%, make it sunny if you forecast more. So the actual setting we're considering is a setting in which the forecaster produces a distribution over forecasts at every time step. Cool. So formally, for every time step t over capital T days, the learner is going to select a distribution over forecasts. Let's just say it's finitely supported for the sake of this talk. The adversary responds with a binary outcome. Then, at the end of capital T days, for each forecast P, you can compute the true empirical frequency for that forecast. That is, the average of these YT outcomes weighted by how much mass I placed on forecast P at each time. And then I can measure my calibration error, which is summing over the forecasts that I ever played with some non-zero mass, the absolute difference between the forecast value and this empirical frequency. We weight the calibration error based on how much mass I placed on the forecast P. If I forecast 20% rain on the vast majority of days, the calibration error for the 20% forecast should be weighted appropriately. Okay, that was binary calibration. I want to generalize the definition. So in binary calibration, we had this interval from 0 to 1. That was our set of potential forecasts, right? We selected our forecasts from the set. The outcomes belong to the set. The average outcomes are thus also elements of the set. And our error is the absolute difference between forecasts and outcomes. To generalize this, we're going to take an arbitrary convex set P in d-dimensional Euclidean space. Our forecaster will select points in P. The outcomes will be selected in P. The average outcomes will be thus members of P. And we will measure our error relative to some norm. So we call this P norm calibration, right? We define the set P, and we define our error norm. That's going to define our general setting of calibration. So, again, formally for every time step t, forecaster selects a distribution over points in P, adversary responds with an outcome in P, empirical outcome is the weighted average of these YTs, the calibration error is now the normed distance between P and Y bar. Sounds good? So, for example, this generalization captures multi-class calibration, okay? So imagine you're forecasting some event, but it doesn't just have a binary outcome. There's many possible outcomes. Maybe it's like any possible next token in some sort of sequence, My forecasts here should be a probability for every possible outcome. So here, our set of forecasts is the simplex in some d-dimensional space. Our outcomes, average outcomes, will also be, elements of these distributions. And we're measuring our error relative to the TV distance, like L1 norm. So we're capturing multi-class calibration in our general framework. It's just, P norm calibration, where P is the simplex and our norm is the L1 norm. Cool. All right. So let's talk about algorithms for this general setting of calibration. I want to come up with an algorithmic procedure for sequentially selecting distributions over forecasts, guaranteeing that no matter what the adversary does, we're going to have at most epsilon t calibration error over all t rounds of learning, for an average per round of epsilon calibration error. So, what are some ideas here? One thing we could do is take our set of potential forecasts and discretize it. lay some epsilon net over. I have some past work that explores calibration algorithms using this idea, but the problem is that in an epsilon net, the number of points is going to be exponential in the dimension. And thus, any single algorithm that's built on this idea that hopes to get epsilon calibration error is going to require a number of rounds that is exponential in the dimension parameter, which in many modern settings where you're forecasting over a large number of potential outcomes is going to be a deal breaker. So there's been this question for a while, which is it possible to improve the dependence of dimension for general calibration? So this recent breakthrough work by Peng answers this question affirmatively for the specific case of multi-class calibration. So remember, multi-class calibration is general calibration, where your action set's the simplex, your norm is the L1 norm. He establishes an algorithm that achieves epsilon calibration error in a number of rounds that is polynomial in the dimension. But as a trade-off, it is now having an exponential dependence in the accuracy parameter, 1 over epsilon. Okay, not ideal, but again, for these modern applications where we're forecasting over a large dimensional space, having an exponential dependence on dimension at all is a complete deal breaker. So at least here, we can hope to get some sort of constant factor calibration error minimization in a number of rounds that is polynomial in dimension. Okay. In this work, we generalize. We establish the algorithm that we call tree-cal, okay? It is worth noting that our algorithm is very similar to Peng's algorithm, and both algorithms are derived from the tree swap algorithm for swap regret minimization, which comes from another concurrent work between our two groups. But our algorithm, tree-cal, is designed for calibration in general, for any forecast set P and for any error norm that we choose. But more so than being general, our algorithm is universal, meaning that the algorithm is the exact same no matter what P looks like and no matter what error norm we are dealing with. It is going to simultaneously minimize calibration error relative to every error norm at the same time. It does so at a rate, so in order to obtain epsilon calibration error, it requires this many rounds. That is parameterized by this term rho. Okay, what is rho? Rho is the optimal regret bound attainable in online linear optimization. A seemingly unrelated question and an unrelated rate appears in our calibration bound. And we'll talk about why. But for many regimes of interest, this term is going to be polynomial in the dimension, or the entire quantity will be polynomial in dimension, and we achieve this breaking the curse of dimensionality. Also worth noting in this paper, we establish lower bound demonstrating that if you want to get epsilon calibration error, it's going to take a number of rounds that's either exponential in the accuracy parameter or in the dimension. So you can't have the best of both worlds, but we're in this regime where we're hoping to obtain polynomial dependence on the dimension, even with worse dependence on accuracy parameter. Okay, let me explain what online linear optimization is, and then I can explain what rho is, and then explain what we're doing. So online linear optimization is a similar sort of setup to what we're doing in calibration. It's a sequential decision-making setup. We have some action set P. For every time step T, we're going to have a learner selecting a point in P. But now, the way that we measure our performance is going to be fundamentally different. First, our adversary is going to be selecting vectors bounded in some norm. So every single round, the adversary responds with some vector LT. And then we actually incur a loss as the learner, which is the inner product of the LT and PT vectors. And our goal is to minimize this quantity regret, which is our total loss compared to the loss of some best fixed action in hindsight. Okay, so a very different performance measure than calibration. But what we end up seeing is the following. In online linear optimization, if it is possible to obtain an epsilon t regret in a number of rounds that is rho over epsilon squared for some quantity rho, then our tree-cal algorithm will obtain a calibration error of epsilon t in a number of rounds that is exponential of rho over epsilon squared. And note that there's a duality, like the norm that bounds the losses in the online linear optimization is the dual of the norm for which we are measuring our calibration error. Okay, let's look at some examples of what this means. There's the classic setting of online linear optimization, in which the action set is the simplex, is the expert setting. Our losses are bounded in infinity norm, and we know that we can obtain epsilon regret here after a number of rounds that is log d over epsilon squared. So that means that if we are doing calibration over the simplex, and our error norm is the L1 norm, the dual of the infinity norm, then we can achieve epsilon calibration in a number of rounds that is polynomial in the dimension, matching Peng's result. But this is more generally applying, right? We also know that if we're doing online linear optimization over the Euclidean norm ball, and our error and the losses are bounded in Euclidean norm, then we can do this at a number of rounds that is independent of dimension. And that means that we can calibrate over the Euclidean norm ball in a dimension-independent number of rounds. Cool. So the other thing that's insane, though, is that these bounds that are occurring on the left-hand side are coming from different algorithms, right? Like the log d over epsilon squared comes from multiplicative weights. The 1 over epsilon squared comes from Euclidean regularized FTRL. So these are algorithms that use different regularizers. Whereas the rates that we're getting on the right side are all from the exact same algorithm that doesn't even use regularization. So how is this algorithm obtaining somehow the exact rates of all of these different specialized algorithms for online linear optimization? Let's talk about it in the next 5 minutes. All right, tree cal. How does this work? We're going to build a tree of intervals of time, okay? So we're going to assume that t is equal to h to the L for some integers h and L. And we're going to build several layers, okay? Our first layer is going to be, our interval of length t, but split into h block intervals of each of length h to the L minus 1. The second layer of our tree is going to be splitting time into h squared intervals. The third layer of our tree, h cubed intervals, etc. And our algorithm, over the course of its runtime, is going to label each of these intervals with a forecast, okay? And how the algorithm works, the forecasts are going to be elements of P. And how the algorithm works is that for a particular time step t, which you can represent as this vertical line, the actual distribution over forecast we will play is simply going to be the uniform distribution over the L layers of the forecast of that layer. The label of the interval containing t at that particular layer. Okay. And so we're going to label these layers we're going to label the intervals in an online fashion. As time progresses, we're going to label the intervals as needed once we reach the first time step where we have to produce a forecast involving that interval. So the last question that remains is, how do I label these intervals? What is the algorithmic procedure? And it's very simple. Essentially we have these intervals arranged into blocks, right, which are like the siblings in the tree. When we're deciding what to label this interval, we simply look at the average outcome that has occurred thus far in this block. And that's how we label the interval. So this interval here would be labeled according to the average outcome over these many rounds, etc. Once you reach a new block, you can label the interval arbitrarily, and then start to label again from the average outcome up to the start of the block. All right, that's the entire tree algorithm, labeling intervals in an online fashion according to these averages over the block. How could this algorithm possibly obtain all of these different rates of all of these different optimal online linear optimization algorithms? Throughout the algorithm, we perform this computation, which is just simply averaging outcomes over some interval of time gamma. The thing is that after the algorithm is done, when we're analyzing the algorithm, we can take many different hindsight perspectives on what this computation was doing. So for example, one thing I could say is that, yes, when we were computing those averages, we were actually computing forecasts that minimize mean squared error, which we know happens to be accomplished by the average. I could also say, yes, when we were computing those averages, we happened to be selecting forecasts to minimize KL divergence mean error, which we know is also optimized by the mean. And these are all more specific instances of a general thing known as proper scoring rules, which is the statement that for any Bregman divergence, we know that the mean is going to be the thing that minimizes the mean Bregman divergence error. We don't know what a Bregman divergence is. It's parameterized by some sort of convex function R. If I have 2 points P and Y and I want to measure their divergence, I simply take the hyperplane tangent at P and ask how much separation do I have from Y, and that's the Bregman divergence. So mean squared error is Bregman for Euclidean norm squared. KL is Bregman for negative entropy function. Okay, so anytime I have a Bregman divergence, I can represent the average Bregman divergence from P to a set of Y's as just the difference from P to the average Y bar, and then the variance of Y bar, right? So this is kind of this generalization of the bias variance decomposition. Okay, what can you do with this? So I can analyze tree cal in the following way. We have forecasts for each interval. We can compare these to the average outcome over those intervals. I'm going to actually take the norm squared. I'll consider squared calibration error for a second. If I take a function r that is strongly convex relative to this norm, I can upper bound this quantity by a Bregman divergence by the definition of strong convexity. And then, because this is a Bregman divergence to a mean, I can decompose this. Oh, also worth note, there's another paper at this conference by Loa, Senapati, and Sharon that also uses this idea of Bregman divergence calibration error measuring. But we can decompose this Bregman divergence into the average divergence to the set of y's of the forecast p and versus the average Bregman divergence from y bar to the set of yt's. You can essentially take every cell of the tree and write out this into this decomposition, upper bound, and then these terms are going to telescope going down the tree. Essentially, the Bregman error of the y bars at label 1 are going to be comparable to the Bregman error of the p's at layer 2. You can upper bound this and save a factor of h going all the way down the tree. So for a total of t over h calibration error, all that remains is the Bregman error of the first layer. In general, this can be arbitrarily large, so we make an additional assumption on r, that r has to be Lipschitz. Then we can upper bound these by rho t, if the quantities are rho Lipschitz. But remember that this term appears in the calibration error with a factor of 1 over L, because we weight our calibration error by how much mass we placed on a particular forecast. So because there's L layers of the tree, and we were uniform over the tree, we save this factor of L. In total, we have this like t over h plus rho t over L calibration error. If we're upper bounding this by epsilon t, then as long as h is at least 1 over epsilon and L is at least rho over epsilon, then we achieve squared norm calibration error in a number of rounds that is this. And by applying Cauchy-Schwarz, we get regular norm calibration error in this number of rounds. So to summarize, as long as this function r exists, I don't have to know what it is, but as long as it exists somewhere out there in the universe, I know that tree swap obtains this calibration error in this many rounds. But this is the exact function r that you're also looking for when you're choosing a regularizer in online linear optimization. So for online linear optimization, you specifically need to find a regularizing function that is strongly convex and bounded, or Lipschitz, in order to run your algorithm. But this is the exact same function as what we need, but we don't actually have to find it. All we have to do is know that it exists to be able to retroactively prove that tree cal got good calibration error relative to that norm. But more so, we know that there's actually an equivalence result for the sake of external regret minimization. Like, if regret is possible, it is possible through a follow the regularized leader algorithm. So if the regret is attainable, then R exists, then tree cal gets the desired rate. Incredible. That's all I had to say. Thank you so much for listening.